would like to thank the organizers to let me this opportunity to give a talk. Very happy about that. Okay, so let me start. So my talk will be on invariant foliations, but also on complex dynamics. So they are a bit different, but they will be have a common point in the talk. So my aim is the following. So I will first talk about invariant foliations, give you some definitions, examples, and then I will introduce you to complex dynamics. So my goal is to show you a theorem that I obtained during my thesis, which asserts the following. So take an endomorphism of P2, F, and there is a special measure that I will introduce to you. And if you have some hypotheses on this measure, then I will show you how to construct an invariant foliation for F. This is my goal. So let me start by holomorphic foliations and variant foliation. So on P2 or CP2, there is a very short definition of foliation. So you just need one holomorphic form, and it gives you a foliation on C2. And if you take polynomial mappings P and Q, then you get an extension to CP2, and how you can describe all the foliations of CP2. And the leaves will be given by the integral curves of the vector field V dual to the form omega. Okay. And what is important in this talk is a formula. So it's a very efficient way to define invariance. So if you pull back the form omega by F, then you will get a new form, and so you will get a new foliation. And this equation is asked exactly that your new foliation coincide with the previous one. It's the notion of invariant. So here F is a mapping on C2 or P2, whatever. Okay, so let me give you very basic examples, but that will be very important in my talk. So here it is the first one. So take a pencil of lines to a point on C2 or P2. Then you have this angle, theta, that is constant along the leaves. So if you take the differential, you will find this form, so up to a function, of course, and it will give you the form that defines this foliation. And you can check that a mapping preserves this foliation on P2 if only if it has this specific form here. So what is important is that the two first functions that defines F only depends on two variables and not the third homogeneous variable. So this is my first example. Another very basic example, but that will also play an important role in my talk, is this trivial foliation, just horizontal lines in C2. So there is a lot of course, a lot of mappings that preserve this foliation. For example, this linear map. Okay, so it's very very basic, but as you will see at the end of the talk, it will be a very crucial foliation for me. Okay. Another thing that I need is a classification of holomorphic foliations that have been obtained 10 years ago. So there is some papers on invariant foliations by Marius Dabija and also Matthias Johnson. And there is also other papers by Favre and Pereira, so on endomorphisms preserving foliations, but also webs. So here, I just speak about foliation. So I give you just a simplified version of the classification because I do not need something too much complicated. So morally, what I want, it's this alternative. So if you take an invariant foliation, it could be a pencil of line, of course. But if it's not, then the mapping F have a very simple form up to choose well your homogeneous coordinates. So in fact, F will be almost a power map. So you can have also a third polynomial mapping that could be more complicated. Okay, so that's all I need for invariant foliations. So now I will turn to complex dynamics, and I will introduce you my theorem. So in complex dynamics, we need invariant object, of course, and there is a canonical way to define invariant objects for holomorphic mappings. So take F that is not invertible. Then you can consider the limit that is written here. So omega P2 is a Fubini-Study form. In general, it's not invariant by the map F, of course. But if you take some pullbacks and some renormalization, then you can show that the sequence converge in a certain sense to a form T. So, of course, it's not smooth. It is a generalization of differential form that we call current. But for my talk, you can imagine that it is a positive form. I don't need to enter into details of current. Just assume it is a positive form. So in particular, you can take its power, and you get, so not really a function because it's not smooth, but a measure. And this current and this measure satisfy invariant relation, as you can see here. And in particular, the measure is invariant. So these objects are very classical, and they are strongly related to the dynamics of the mapping. So, for example, the support of this object are exactly what we call the big and the small Julia sets. So the big Julia set is the complementary set of the Fatou sets. So the Fatou set, as you may imagine, is a set where the iterates of F have a good behavior, and these sets are where the dynamics is more chaotic. And the Julia set is where the dynamic is most chaotic. The small Julia set. Okay. So when we are in the smooth case, the situation is very well understood. So we have this equivalent points. So if you ask T to be smooth, then it's equivalent to say that the measure is absolutely continuous with respect to the Lebesgue measure. So the Lebesgue measure is just a class of volume forms. So you can take the power of the Fubini-Study form. And it also corresponds to lattice mapping. So I will give you a definition in a few seconds. Okay, so I'm not really interested by Lyapunov exponent in this talk, but I can mention that there is a link between the Lyapunov exponent of the measure mu, that in fact is an ergodic measure, and it's also the measure of maximal entropy of the mapping F. Okay, but I will not speak about Lyapunov exponent in this talk. What is important here is that you can use the Favre-Pereira classification to observe that F cannot preserve a foliation. Okay, it's because it is lattice. So it is not the kind of mappings that are interesting in. So I will turn now to cases where T is not smooth. Okay, but just before, let me give you a definition about lattice map. So lattice mappings can be defined as follows. So here I give you an example in dimension 1 because I will take a lattice map of 1 dimension in the rest of the talk. So the definition is the following. So if you take a rational map theta of degree d, then it is lattice if you can lift it to some affine map. So here it is linear. And you have, and the definition is that you need the linear part to be a multiplication by the square root of the degree of the mapping. And the vertical map here has to be some covering, holomorphic covering map. So here, for this particular historical example studied by lattice, you can take the Weierstrass function. Okay, so on higher dimension, it's the same definition. So on pk, if you have an endomorphism of pk, it is lattice if you can lift it as this example to an affine map on ck, but with a linear part that is just a multiplication by the square root of d. Okay, but I will just use lattice mappings of 1 dimension in the rest of the talk. So why? Because as I told you before, lattice map of P2 cannot preserve foliations, but some kind of semi-lattice mappings can. So take a lattice map on P1, theta, and extend it to P2 like this. So we call that a lattice suspension. Then we understand very well the dynamics of these mappings. Near repelling fixed point, we can linearize the map as follows, and we can give a precise description of the current. So if you are on C2, the current is, you can replace it by an Hermitian matrix with, but not composed of complex numbers, but composed of complex measures. So on the diagonal, you have positive measures. In this particular example, the over diagonal is null, but it's not the case in general. And what is important is that there is this special formula that tells you that the measure is the first element of the matrix that defines the currents. So this is a very special formula. But it is really interesting. And why? Because you can prove the following. So this is my theorem. So take the formula we just have seen. So with an invariant coordinate, and assume some other hypothesis that I will describe later. Then it is possible to create an invariant foliation that lives on a neighborhood of the big Julia set. So minus this special set that I will give you a definition in a second. And if you are able to do that, then if you are moreover able to extend a little bit the foliation through this special set, so it is an algebraic set, I will give you the definition in a few seconds, then you can show that the foliation is a pencil of lines. So I will go, before continue, I give you the definition of the set EF. So it is called the exceptional set. So this is, in fact, the largest totally invariant algebraic set of F. And you can also define it as follows. So it is a set of point X on P2 such that the pre-image of the iterates of F do not equidistribute to the measure mu. And as I told you, it is an algebraic set, so you can show that it has 0 measure. Okay, so here you have some picture of the dynamics of lattice suspension. So in fact, lattice suspension satisfy all the hypotheses of my theorem. So let me describe it very briefly. So here you have a basin of attraction, and the boundary of the basin is the small Julia set, the support of the measure mu. And the complementary of the basin, is the support of the current. Okay? So here I have drawn the lines of the pencil that is preserved by F. And in this case, my foliation is exactly this pencil. Okay? And so for the exceptional set, EF, in this example, it is the center of the basin and the line at infinity. Okay. So just for sake of completeness, I can mention that if you take a mapping that preserves a pencil line, but not necessarily a lattice suspension, but if you ask on the pencil that you have a lattice map, then you can show that you always have my formula that I ask in my theorem. Maybe not for fixed point, but for at least for repelling periodic points. Okay, so this is just for sake of completeness. So now I will turn to the proof. So I will not enter into every details, but I will give you the general strategy for the proof. So I recall the statement. So we are going to start with this formula, and we are going to globalize it a little bit, because for the moment, I have to mention that this formula makes sense just only at the neighborhood of the fixed point A. So how we can do that? First, we construct a second submersion that allows to linearize a little bit the dynamics. So I just mentioned that here I don't have necessarily a linear map in general. You can have a polynomial map, but whatever. It's not a big deal. For my talk, I choose the linear case for the first coordinate. For the second coordinate of the map above, you always have this kind of linearization up to a complex number of modulus 1, of course. And so you can always do that. This is an application of Poincaré-Dulac linearization theorem. But in my case, you have something that is new. It is this formula. So you take the formula near the fixed point, and you pull back it near 0 in C2. And then you can globalize it using a classical construction that is called developing map or Poincaré maps. So because your fixed point is repelling, you can use the definition that is here to define a mapping sigma that extends your local diagram into a global diagram on C2. And you can also show that the local formula between mu and t near 0 in C2 extend into a global formula on C2. Okay, this is a complex, this is positive measures on C2, but be careful, they have infinite mass. And then to create a foliation, we do the following. So we study the fibers of sigma. So here I take a point in P2 that belongs to the big Julia set, and I consider two pre-images, X and Y. So let me ask that these points are not critical points. So you can also deal with critical points. This is not too much difficult. And since they are not critical, you can create local inversion of sigma. So I call them sigma X and sigma Y. And you can look at the map that goes from x to y by doing sigma x and then sigma y minus 1. So you can always do that in general, but here, because of this formula, we get something by pushing forward the formula by sigma x and sigma y, and we get this formula that gives you a description of the measure mu, the current t, with respect to the two local coordinates associated to the inversion of sigma y and sigma x. And so why this is interesting is because we can patch these coordinates. So this is where my other hypothesis of my theorem appears. So we can show that the differential form of the coordinates are equal modulo nowhere vanishing holomorphic function. And thus, in corollary, we get that the mapping going from x to y has a special form. It has a fibered form. Okay? So since you have this kind of form, you may imagine that a foliation will appear. Okay? Take horizontal lines in C2, and because the mapping has this special form, when you take the image, you will get some holomorphic disk that will patch together to create a coherent foliation defined on neighborhood of the point P. So this is why my horizontal foliation on C2 is important. Because when we take images by sigma, it's glued together to define a foliation. So here it is local, but you can do it for every point, and then all your local foliation will patch together to create a coherent foliation that coincides with the image of the horizontal foliation of C2 by the mapping sigma. And then you have almost finished. You need to show that it is invariant, but it is not difficult since F is semi-conjugated by a linear map that, of course, leave invariant the horizontal foliation, like I have explained to you at the beginning. So it's how you can prove the first part of the theorem. So if I go back to the theorem, I have proved the first point. And if you want the second point, if you want a pencil of line, you have first to extend the foliation through the exceptional set. And if you are able to do that, then you can use the fact that the complementary set of the green current is Stein. And this is a result of Lins-Netto. If you are in this kind of situation, then you can extend the foliation. Okay? If you have a compact set whose complementary set in P2 is Stein, and if you have a foliation defined on a neighborhood of this compact set, then you can automatically extend globally the foliation on P2. This is what I call Lins-Netto theorem. And then at the end, you have a global foliation, but using again Favre-Pereira classification, you can deduce that the only possibility is that you have a pencil of line because of the special property I have assumed in the statement of the theorem. And moreover, you can check that the map that is induced on the pencil is lattice. It is a lattice rational map. Okay, so that's the global strategy, and I think I can stop here if you have some question.
Thank you. Are there any questions?
Any question here?
First question. So your foliation in your statement is holomorphic foliation.
Yeah, yes, of course, yes. Yeah, so what we expect, in fact, is that this foliation should be always a pencil of line. So, okay, so if I go back to M, I have this hypothesis, so I did not mention too much, but we expect that this hypothesis should be automatic, but we are not able to prove it for the moment, but we really expect it. And so the only solution to get a pencil of line that appears is the exceptional set. This set. If this set has a so it will always, of course, meet the support of the current if it is not empty. But we do not have. Actually, I do not have any other example that than this kind of mappings that satisfy that preserve a foliation with that kind of hypothesis. So we expect that so lattice function, or more generally, this kind of mapping, so that preserve a pencil of lines with a lattice map, are the only example that satisfy the formula that is here. But we are not able to prove it anymore. But we expect that maybe this formula itself is a characterization of mapping preserving a pencil of line with a lattice map on it.
Questions here? Do we have questions? Anyone? And I don't think we have any from this side of the Atlantic.
So now we can come with